pleasure to introduce Markus Müller. He's going to be leaving us for the University of Vienna. We very much missed. He's going to be speaking on operational interpretation of entropy and free energy without the thermodynamic limit.
Okay, thanks very much. So thanks to Wayne for inviting me. It's really nice to be back at Western in the philosophy crowd. So I'm really happy to be here. I'm enjoying this conference a lot. I'm not talking about guitars now, but about how we can operationally interpret the free energy and also entropy without going to a thermodynamic limit. Now, when I say entropy, then I mean the von Neumann entropy of quantum states. And this is, I would say, a fundamental result, and some of it is based on work I did with former students of mine, with Michele Pastena and Jakob Scharlau, and also some work with my colleague Matteo Lo Saglio. Here's a quick outline. So you should recognize this picture. It's very, very similar to what Nelly has talked about. And I will, in fact, repeat a few things that Nelly said as well. And I'm quite happy that she prepared the stage in some sense by explaining a few things to you that I may actually use in my talk. So in the first part of my talk, I will give you the standard view on entropy, which is basically that entropy becomes only meaningful in a thermodynamic limit, when you have large systems, many particles, or you do averaging. Then in the second part, I will introduce thermodynamics as a resource theory in the same way that Nelly talked about it. So I will repeat some of it and also put this in context to the first part. The third part will be the actual result, which gives you some kind of new one-shot interpretation of the free energy and the entropy. Now, one shot here is always to be contrasted with many shots or many particles. So it's something that you do with a single particle in a single cycle of an engine and not in the thermodynamic limit. Now in the last part, that's a bit work in progress and some speculation whether this might tell you something more fundamental about quantum information in general. Okay, so let's start with the standard view. In the following, I will always look at a scenario where we have a fixed background temperature T. And in a standard box in a gas paradigm, we would also have a fixed volume, for example. And then there's this folklore idea that you learn very early in the physics studies that if you have spontaneous thermodynamic processes, then these spontaneous processes will always decrease the free energy. So it's the Helmholtz free energy U minus Ts that's relevant in the setup. And this free energy can never increase spontaneously. If it decreases, then sometimes this means that you can really extract useful work from the system. Yeah. So by computing the free energy differences, in many cases, this will tell you how much work you can extract from a system via a heat engine, for example. But all these statements, as we know from statistical mechanics, and if we just look very closely at our thermodynamic systems, are just statements on average. On average means we average over a large number of particles and we go to the thermodynamic limit. Actually, work, as we've heard before many times today, is a random variable. So if you have a fixed process, then, for example, you have a gas in a box and you insert a piston, you try to raise a weight, and then you ask in the end, by how much did I actually raise the weight? Then the amount of work that you get out from such a process fluctuates. So in general, it is a random variable. Yeah? You have a certain probability distribution over the different possible values of work. And now, in standard thermodynamics, we usually have systems that are so large that, in some sense, the law of large numbers kicks in. So the distributions that we have, for example, over the different values of work that we could extract, are just very, very strongly peaked around the averages. So if n is, for example, a particle number, then the free energy would be proportional to the number of particles, but the spread would be really something like the square root of the particle number. So we're strongly peaked around the average. And that means we can just replace the values, like W, just by the averages. That's what we do in standard thermodynamics. And this is where the standard prescriptions that we learn in standard thermodynamics will really apply. So when we say that in some processes the extractable work is really given by the difference in free energies, then this is a statement that's only true in a thermodynamic limit where the number of systems involved or particles is going to infinity. because then these fluctuations will actually become irrelevant. They won't really matter. And the law of large numbers is basically what tells you that. Now, the question is, and this is also one of the motivations to really look at these resource-theoretic approaches, is to say, but what happens if we really have just one particle or a few particles? So what if you have small quantum systems? Or maybe we have many, but they are strongly correlated, so that we cannot just say it's like having a large ensemble of independent particles. What do we do then? Then we have a problem, namely the work that we really get, for example, in a cycle might have so strong fluctuations that the amount that it fluctuates is actually comparable to the actual amount of work that we get out. So that relates also to what Nelly said about the weight that you raise, and then classically, in usual thermodynamics, it doesn't really wiggle very much. So you can neglect the fluctuations, but in the quantum regime and for small systems, you cannot really neglect these fluctuations. And so let me see. Now, when you actually look at small systems, then we find that the free energy can sometimes tell us something, but it will not always tell us the full story. So here's an example called Lando erasure. You start with a system which has two possible configurations. For example, a particle where you don't know if it's sitting in the left or in the right of this potential. And what you want is you want to do a process that resets the particle to be definitely with probability 1 in the left half, for example, of that potential. Now, can we do that just for free? So can we basically erase this bit for free? Well, Lando's principle tells us that it's not possible. And to see why it's not possible, all you have to do is to compute the free energy difference. And then we'll see that in this process, the free energy has to go up. So this means that this process cannot occur spontaneously. We have to invest some work to do it. And the free energy really tells us that this is the case. Now this looks all fine. And this is one way to see why erasing a bit costs you energy. But then you can make things a bit more complicated and, for example, look at a puzzle that Bennett has come up with. So let's say you don't have only two possible configurations, but many others. And the left two, these two, still have probability 1/2, and then you know that the others are not occupied. So that's basically the same as here. You just introduce a few empty slots. And then you think, well, maybe I cannot go exactly to this reset state where I know the particle is, but maybe almost. So maybe it's like with 99% probability there, and then with 1% probability spread over all the rest of the levels. That would also be pretty good. It would be pretty good resetting of your system. But if you compute the difference in free energy, which amounts to computing the entropy difference of both sides, then you find if n is really, really large, then the entropy can actually go up in that process, and so the free energy can go down. So suddenly this criterion will tell you that this is a possible transition. So that's something that could, in principle, appear spontaneously, even if epsilon is very, very small. And this would be really surprising. So why don't we see these processes happening in nature, or how can we rule them out? That's what I call Bennett's puzzle here. So Charles Bennett has come up with something like this before.
Why is it surprising?
Well, so if epsilon is like 1 in a million, yeah, and you're having this bit that you want to erase, then just give yourself a few extra levels, or maybe you have them already. And then if you just wait, and then suddenly, after a while, you're almost sure, up to 1 in a million, that the particle must be in this slot. That's just not something you would expect to find. It's very close, in some sense, to the standard Lando erasure. Of course, there are subtleties, and I'm going to these subtleties now. All I'm saying here is that the standard condition of the free energy decrease cannot really rule this out. But we will see that there are now, if we look at, so okay, as I said, the free energy determines the possibility of state transitions only in a thermodynamic limit, so we cannot really apply it to the situation. So for small systems, we will get additional constraints, which are these constraints that also Nelly talked about, and they will indeed solve Bennett's puzzle and rule out that such a transition is possible. So I will come to that in a second. The insight that standard entropy and standard free energy only apply in a thermodynamic limit also is reflected in information theory. If you ask about the meaning of entropy, for example, for data compression, then here's the usual story that people tell. So to see entropy, on the meaning of entropy, you need n copies of a quantum state. So you have n independent copies of one state. And what you want to do is you want to compress it to a fewer number of quantum systems. Now you ask, how can I do that? Well, one way to do it is to say I want to project it into some subspace such that the probability to be there is almost 1. It's 1 minus epsilon, and epsilon goes to 0. And the subspace, the dimension of the subspace should be small. I want to compress it to something smaller. How small can I make this? And then it turns out the smallest value that you can get, if you take the dimension of a subspace and take the log, is basically n times the entropy plus some small corrections. And S is exactly for Neumann entropy, so trace of rho log rho. So what this tells you that is if you want to compress quantum information in the limit of many copies, for Neumann entropy tells you how well you can compress your state. But it's only in the limit of infinitely many copies. So it's not true if you have just a single quantum state or strongly correlated quantum states. So this is basically what the standard view in quantum information in thermodynamics on these quantities, that you have to have large ensembles to see the entropy at work. Good. Now, how does it fit into the resource-theoretic framework? What does it tell us for single copies of quantum systems? So here's the paper that Nelly also talked about, who's also here. So in order to talk about thermodynamics for small and strongly correlated systems, you would like to formulate it as a resource theory. And this is the picture you've also seen in Nelly's talk. So what you do is you say, well, I have some initial system, initial state, and I want to transform it to some final state. And to do so, I allow a thermal reservoir, so this is the thermal bath, and some energy-preserving unitary. And then what we also, and I've seen this in Nelly's talk, can do is we can borrow an extra system from somewhere, a catalyst. So we borrow the catalyst, it's somewhere involved in the process, and we get the catalyst back in the end, unchanged, and can give it back to the bank, for example. So these would be processes where you say, I have my state of my system, I have the thermal state here of the reservoir, and I have a catalyst state, and then let's do a big unitary on all of them, and this unitary should be energy conserving, so it should commute with the total Hamiltonian. And when we do this, and then we forget the thermal reservoir, we just trace out the bath, we want our new state, and also we want back our catalyst in the end, which is the same as we had before, so the catalyst doesn't change. Now, what are the rules of the game of resource theory? So the rules of the game, as we've heard before, are what are the free operations? And the free operations here are that you're always free to bring in a thermal bath. So some system which is in its thermal state. So whatever its Hamiltonian is, the state of the system will just be the Gibbs state. Then you're allowed to do strictly energy-preserving unitaries. And then you can also discard systems. Yeah, you can basically throw stuff into the thermal bath and forget about it if you want. And anything that's not thermal is then a resource. So the advantage is this is really a clear game with clear rules. It's just mathematically really rigorous, and you can work out what's possible and what's impossible in this framework. And this gives you really nice insights sometimes on which transitions are possible, what kind of efficiency can you have for heat engines, and so on. So what you also find, that's also maybe a nice insight of the resource theory, that if instead of a thermal state you allowed another state to be free, then the resource theory would just become trivial and everything would be possible and all transitions between all states would be possible. So that's like an indirect justification of the Gibbs states and why they're important. That's related to what Owen talked about complete passivity of the thermal state. Good. Now, we've set the rules of the game. We now know what our resource theory are, and then we can work out what kind of transitions between states this theory allows. So suppose you have initial state rho of your system here. You want your final quantum state rho prime. When can you get from rho to rho prime by a process like this? And now this has been fully characterized in the case where both rho and rho prime are incoherent, so where they are block diagonal in energy. Now this is of course a restriction. It means you have states which are quasi-classical, but it's good enough to talk about Lando erasure, for example. In Lando erasure, as I've talked about, you just have probabilities 1/2, 1/2, and you don't have coherences between these levels. So that is covered by the setting. So for block diagonal states, it turns out that you can say exactly when such a transition is possible, namely the free energy, the alpha free energy of your initial state must be larger than or equal to the alpha free energy of your final state. And this must be true for all alphas. So these are exactly the free alpha, the free energy that Nelly has talked about. And in the case that alpha is equal to 1, it turns out that this is just the standard Helmholtz free energy. So the free energy of a state rho is just the expectation value of the energy minus temperature times von Neumann entropy. Yeah? It's U minus Ts. That's again just the standard free energy. For all other alpha, there's an equation that gives you that. And what you do is you have to compute a certain relative entropy between the state and the thermal state, namely the Rényi relative entropy between these two states. And all these quantities, for all real numbers alpha, they all have to go down. Good. Now, first thing to see, maybe just for fun, as a warm-up, is to see that this really solves Bennett's puzzle. Again, as I said, it would be surprising if a transition like this for very small epsilon would be spontaneously possible. The standard free energy difference, Helmholtz free energy difference, is negative. So that suggests that it's a possible process, but we just agreed that it actually should be impossible. And indeed, we will find that it is impossible according to these alpha free energy conditions. So in this plot, you will see the difference in free energy alpha for the different alphas. And now for alpha equal to 1, as I said, here is the standard free energy, and the difference is actually negative. So that would tell you, maybe it's actually possible. But for larger alphas, you see, the free energy to alpha difference is actually positive. And since it's positive, it violates the condition, and it tells you that this here is an impossible transition. Yeah? So in this framework, according to the rules of the resource theory, it is impossible to transform a state with these eigenvalues, these probabilities, to a state with those probabilities. Good. Now, what about work extraction in general, or the opposite? We want to perform some work on a quantum system and ask how much work do we have to spend. So as I said, in both cases, work is a random variable. And here is a paper where, it's Horodetsky and Oppenheim, and they have worked out what the extractable work and work cost is in this resource theory. Now, in order to model this, you have to say what you mean by work, as we've heard before in the talk. And one way to model work in the quantum regime is to say, if I want to extract work, what I do is I have this quantum system in the ground state, and I just raise it to the excited state. It's like a weight that I raise. That would be work extraction. Spending work would just be the opposite. It would be going from an excited state to a ground state. So in addition to the other setup, you will have this, what people call work bit, and you raise it or you lower it to spend or to extract work. Then you can ask, well, how much work can I get here? Or how much work do I have to invest? If this is the energy difference here is W, what is this W? And one way to say it is the following. You say, well, maybe I don't get exactly the excited state, but maybe I get very close to the excited state. So in order to have a reliable amount of work in the end, I want a very high probability of ending up in the excited state. Maybe it's larger than 1 minus epsilon, this probability. Then you can work out what this means, and it tells you that if you have a state rho, then the work you can extract from it in the end turns out to be given by this Rayleigh free energy again. And in this case, the 0 Rayleigh free energy. Yeah. There's a little epsilon, which tells you that it's a certain version of this Rayleigh free energy where you allow an epsilon error. Also, if you say, what if I just have a thermal state and I want to create a state rho? How much work does it cost me? It turns out that it's F infinity, so it's for alpha equal to infinity. One other of these Rayleigh free energies that tells you how much that is. And in general, you'll find that F0 is much smaller than F infinity, and the standard free energy is somehow in between. So this tells you you need a lot more work to create a state. And if you have the state and you want to get back that work, you can only get back part of that work. Yeah? So this is like a fundamental irreversibility that you get in this framework if you work on a single quantum state. Now, however, and it's something I guess that Rob has shown first, the nice thing is that in the thermodynamic limit, in a certain sense, you recover standard thermodynamic prescription. In this case, the simplest setup where you say this is like the thermodynamic limit is to say you have n copies of your state, many independent copies, and then you ask what's the work cost in extractable work, and you evaluate these F0 and F infinity and say divide it by the number of particles, and that turns out to just converge in the limit to the standard free energy, to the usual Helmholtz free energy. So this tells you that in the thermodynamic limit, finally, if you allow a little bit of error, but you have a large number of particles, you really get the standard thermodynamic prescription that it's the standard free energy that has to go down. Again, here we have a situation where F becomes important, but in the thermodynamic limit. Okay. Now, what all this suggests is that von Neumann entropy and free energy are really for many particles. Yeah? Can we have a meaning of them for one particle? That will be something I'm talking about now. So this is in this paper here, which relies a lot on some earlier work with the students I've shown you. So here's a picture of the setup, and it's very close to the one we've seen before and also Nelly's talk. So we have our system initially and our system finally, and we want to do a transformation. We also have a catalyst that we can borrow and that we have to give back unchanged. And one way to think of a catalyst is really it's just part of your thermal machine. Yeah, you have your system, you put around a big thermal machine, and you do a thermodynamic cycle. And part of that machine is this quantum state. And since you want to preserve your machine, you also want to preserve that quantum state here. Everything happens in a thermal bath, so you have a thermal operation all in all. You have a work bit where you can spend work or extract work. So that's exactly as before. But now there's something new. So what we do now is we say, well, what if we allow that there are correlations that build up between the catalyst and the system? So that's different from Nelly's setup, as Nelly mentioned in her talk as well, because in Nelly's setup, we would have them uncorrelated and decoupled in the end.
So the sense in which we get the catalyst back unchanged is the marginal state.
Exactly, yes, exactly. It's the marginal state, so if you trace out everything here, the marginal state of the catalyst is exactly the same. Yeah. Now, when is that a good model? So I'm not saying that this is somehow better than Nelly's setup or anything. It depends on the situation you want to look at. And I guess here's a situation where correlations are okay. So think of a small biological machine maybe here, yeah, and the machine is acting on small particles, single particles, one after the other. Maybe it's like a stream of particles that's just flowing by, yeah. And then the machine is acting on one particle just goes away and never comes back. Then it's acting on the next particle, it goes away and never comes back, and so on. So then all that you need is that your machine is preserved so that this quantum state just stays the same locally, but you can have correlations built up with these systems that just go away. that's perfectly fine for some situations. In some situations may not be fine, and you may want to actually have them decoupled. For example, when these systems become correlated with a machine, they become indirectly correlated with each other. And maybe this is something that you don't want, because maybe there's a goal that these particles have to do something else elsewhere. But if this is not the case, then we can really allow these correlations in the first place. The question is, if you allow this, can this really help? And the answer turns out to be yes, this can help. And here's a little example. So let's just first look at the standard setup, where we have a system that we want to transform, a work bit where we spend energy, and a catalyst for the machine. And the catalyst can be anything, and it must remain product with everything else. Okay, that's the standard setup that we heard about before. So A now is just a qubit. It's a two-level system, and it starts off in its thermal state. So thermal state, in this case, where you have energy 0 and energy, well, in this case, it's chosen like that. It doesn't really matter. But it turns out that the thermal state will be 2/3 for the ground state and, say, 1/3 for the excited state. And what we want to do is we want to change the state and heat it up so that the probabilities become 1/2 and 1/2. That's the goal. And this is not free, so we have to spend energy to do it, and we will draw the energy from this work system. It starts out excited with some energy difference delta, and it ends up in the ground state. Now, all in all, we want a transition like this. So we have the thermal state on A, we have the state of the machine, of the catalyst, and that will be the same initially and finally, and the excited state going to the ground state. Now, what do we have to check and to compute? Well, we have to compare the alpha free energies of the left-hand side with the alpha free energies on the right-hand side. And for all alphas, this has to be, the left-hand side has to be larger than the right-hand side. And if you work that out and compute the alpha free energies, you find, the smallest possible amount of work that you need to do that is just 0.4 Boltzmann constant times the temperature. You can just work that out. Now, if you just compute the standard free energy difference, you would find, actually 0.06 kBT should be enough. But we've just seen that the standard free energy is not sufficient to tell us what's possible. We have these extra constraints. And these extra constraints lead to the fact that we need more work than we would naively think we did. Now, what if we modify the setup and now allow correlations to build up? And here's an example where you see that this can really help. So our machine, our catalyst, is now also a qubit. It's just a two-level system. And the two energies of that system are just the same, so there's no energy gap. And it will start in the same state as it ends. But in addition, you will have these two systems become correlated. And the local state on A is really the one we want, and the local state on M is just the same as before. So you would have a transition like this. You start thermal state on A, the state of the machine, excited state here. You go to this new state on MA, and the ground state on the work system. Now, how do you do this? Well, here's an example how you would do that. I'm not sure how illustrative that is, but it's an example here. So this is a state of A and M, so of two of these qubits, your machine and the system. And it turns out to be a correlated state of the two. So there's a probability of 1/10 that you have the ground state on A and the 0 state on M, and so on. Now you will find that when you compute the state on A, so you sum over M, so you sum over this here, gives you 1/10 plus 4/10 is 1/2. You sum over that, you also get 1/2. So you get really the state that you want on the system A. And if you sum in the other direction, you will get the state on M, which is just the same as you had initially. So 1/10 plus 3/10 is like, so that's like 3/10, and the other one would be 7/10. So that would be the state of M. So that's a possible transition. And it turns out that this transition can really be achieved by a thermal operation. You can really do it. And if you do it and you ask, well, then how much should this delta be? How large does this energy have to be that I invest? Turns out that 0.26 kBt is enough. And before we had 0.4 kBt, so we can do better. We can like save some energy. How would you check this? Well, you check that this is possible by using these Lorentz curves that Nelly talked about. You see, oh, here's the initial state, the blue one, and the final state here of the machine and of the work bit is actually below. So yes, it's a possible transition, and it has helped you. Now the question is obviously this. This is just an example, but if I have larger, better catalysts, then what can I do? What are the ultimate limitations and possibilities of this? And it turns out that the ultimate limitations and possibilities are exactly those given by delta F, by the free energy difference. So in this case, we can really go down further until the free energy difference, like 0.06 kBt here, but we cannot go down further. So in this setup, you would have that theorem here. So you can go from initial state to a final state with a process like the one I've shown you for block diagonal states if and only if the standard Helmholtz free energy goes down in that process. Good. So in a way, this gives you a single particle or a one-shot interpretation of what the Helmholtz free energy means. So the second laws that you have in situations where you do not want these correlations, they actually collapse just to the standard second law. Only one monotone, one law, when you allow these correlations to build up. So here's a result here formulated mathematically. So you have your initial states, product, your final state will be, so this is without the work bit. Just say initial state, final state, state on M is the same. The state on A is as close to the state I want, like epsilon close to the state that I want, and epsilon can be as small as I like. And then this is possible if and only if the free energy goes down. Now one thing to note is you can do this, in fact, you can ask how big do these correlations have to be, and the answer is they can be as small as you want, in fact, but they cannot really be zero. Also, here's a conjecture. So this is only for block diagonal states. It's quantum states that have no coherence in them. But we conjecture that this should actually also be true in the presence of quantum coherence. Something similar like that should be true, and that's what we're looking at the moment. Now, yeah, this is maybe a funny comparison. So this is somewhat reminiscent of more old school thermodynamics. Like think of Boltzmann's Stoßzahlansatz, where you have a box of gas, you have particles colliding, and then the assumption is that the particles that collide, that the velocities of these particles are initially uncorrelated and they factorize. But obviously after the collision they will not factorize, and you will naturally get correlations. And this is a bit what's happening here. Yeah. So the system ages, so to say, by creating correlations. What about work cost? So I've just shown you an example where we invested work. What can we say here? Turns out that the work cost of some process becomes really just the Helmholtz free energy on a single particle, and you have exactly zero fluctuations. So this is again what we want. We have initial state, we have the final state, the machine is preserved. You want to get from an excited to a ground state, and then you can do it with an energy that is basically the difference in free energies. A little bit larger, but any value that's larger than the difference will allow this transition. So basically it's delta F that you need. Also the machine is finite dimensional, yeah, and it's exactly preserved. It only builds up correlations with the other system. So in a way, yeah, this is really surprising, I would say, because the system that you send in, that could be a very, well, it's a probabilistic system with a lot of probabilities, with high entropy possibly. And what you get is here a very controlled process where you exactly flip the work bit from excited to ground. Yeah. And there is no probability distribution over the work you spend. You just spend this work exactly with probability 1. Yeah. And you can do this by having a very clever catalyst that allows you to do this on a single copy of your state. I think it's quite surprising that this is possible. Now what about extractable work? extractable work is not quite as nice, unfortunately, and this for the same reasons that in Nelly's work she had to talk about near-perfect work extraction. So it's the same reason. So if you extract work, you can really extract the standard Helmholtz free difference from one copy of your state. But what you need is you have to deal with a little bit of fluctuations that you can not make zero, but you can make them as close to zero as you want. So in quantum information jargon, what you would need is called a max entropy sink. So what you have is you would have a bunch, like a state here, that's your ground state. It has probability 1 for the ground state and 0 for the others. And what you want is you want excited state, but you have to kind of move some entropy, some max entropy to some other level. So, but epsilon can be as small as possible. Let me not go into details here, maybe skip this for now. Let me just say that the fluctuations now cannot be zero, but you can make them as small as you like. And the fact that they cannot be zero turns out to be related to some versions of the third law of thermodynamics, which would, however, be another story to tell. Good. So where does it follow from? Well, here's a theorem on majorization that's basically the workhorse of all of that. So we've seen in the picture, I've shown you these Lorentz curves that tell you whether a transition is possible or not. So it has to do with majorization. And this is a result of majorization that tells you when does a state P majorize another state P prime, but you allowed this catalyst Py prime that remains unchanged. And then it turns out that the standard Shannon entropy and what's called the Hartley entropy, it's a number of zeros or of non-zero entries. They basically tell you whether this is possible or not. But again, let me skip this. Let me talk instead about this here. So this is another way to view the result physically. So that's another way to do this with Matteo Lostaglio. Here's with earlier work, which is a kind of a weaker result, but it's also maybe tells you what the physics behind this is. So again, you ask, if I have a thermal operation, I want to go from initial to final state, can I do this, yes or no? But now I allow this extra process where I have catalysts, maybe 3 of them, and they have to be given back exactly as before, but I allow correlations to build up between them. Can this actually help? And the answer is, yes, this can help, and transitions that you would not otherwise be able to do can sometimes be done if you allow correlations to build up. And one way to see is that you, if you do it without this, you would have strong fluctuations for your work extraction. But when you do this, you somehow move these fluctuations into the correlations between the different parts of your system. And from the point of view of standard thermodynamics, this is actually a bit surprising if you think about that. So if you start uncorrelated and you put in correlations, what this means is you put in free energy into your system. So the free energy of a correlated system is always larger than the free energy of the uncorrelated system. So you would think, well, here I put in free energy, that should make it even harder to do the transition. But it turns out that in this context, it actually helps you and allows you transitions that would not otherwise be possible. Yeah, you can trade fluctuations for correlations in that sense. Good. Now, what I've shown you so far is really about thermodynamics. But we think that this is really just a shadow of some more general properties of von Neumann entropy in quantum information theory. But this we really don't know yet, so this is just speculation. So there might be similar results in quantum information. And usually when you look in quantum information papers, then people consider all kinds of tasks. They say, well, what if I want to do decoupling of quantum information? So like in this paper, I have a big system, correlated. I want to put it in a state that's decoupled, and how much do I have to throw away to do this? And then the answers to these questions always depend on entropic quantities that are like entropies, that are very strange entropies. So like the max mutual information, for example, or these rainy entropies that I've shown you, F0 and F infinity, that are usually the ones that I show up here. But so typically these tasks we ask, I want to do them only once. I want to do them on one copy of a quantum state. What can I do? These are usually the one-shot entropies. But given what I've shown you in this thermodynamic framework, you may wonder whether really, if you just have one quantum state, whether in some settings it's actually the standard for Neumann entropy can really attain some operational interpretation if you allow correlations to build up in your setup in some way. So why is this interesting? So one reason for us to look at this is that you have all these high energy physics people that tell you a story about entropies. Namely, these standard entropies, the von Neumann entropy, has a space-time interpretation. So this is something that some of you may have seen. This is in the context of string theory, where you say, well, I have a field theory, a quantum field theory on a boundary of some space-time. And then I can compute the von Neumann entropy of a region, for example. This is really the standard von Neumann entropy and no other entropy. And now they claim that this has something to do with some gravity theory inside of this, so in the bulk. And they claim, for example, if I compute the von Neumann entropy of something on the boundary, I will find something like the area of a minimal surface in the interior of that region. Now, you ask, why should that be the case? Why is it the von Neumann entropy and not one of these other entropies? And what people also wanted to say, well, here on the boundary, I can give this entropy a meaning. I can tell you something that it means something about data compression on the boundary. And maybe I can go then to the bulk and give it also a meaning, an operational meaning. But the problem is, of course, you need many copies on the boundary to give standard entropy a meaning. But you have only one copy of your space-time. So in this context, what you would really like to have is a one-copy operational interpretation of what S means on the boundary to say something about the theory in the bulk. So what's possible here? So I don't know yet, but I will just give you, well, actually two examples of what we do know. So here's just a very abstract situation in quantum information where you say, I have an initial state, I want to transform it to a final state. And I want to do it by a big unitary operation. Now I have helper systems, catalysts that help me achieve this. So I have some other state that I get back in the end unchanged. And I have a third state, actually maximally mixed, that I also get back in the end. But I allow that they become correlated. What can I do if I allow this? Now, first thing to see is that if you look at the entropies initially and the entropies finally, then you will easily see that the entropy of your blue state here has to go up. It's actually a one-line calculation. So initially you have a sum of the three entropies that's here, and then finally you have this big state, whatever that is, and that's the same entropy because the unitary doesn't change the entropy. And then there's a property called subeditivity, which tells you this is less than or equal than the sum of the entropies. And you see that this means that on A, the entropy has to go up. So this is necessary, but is it sufficient? It turns out to be actually sufficient here. So if and only if the entropy goes up here, can you do this process? So this is already an example of a single shot or one particle meaning of the von Neumann entropy. Now, obviously what you would want to have here is that we don't have three systems, but just two. You really just have a catalyst, you do something to your system, you get your catalyst back, and you can use it on other systems. And here's a conjecture that we think is very natural, and we were very surprised to see that nobody has looked at it. So namely that the von Neumann entropy has the following meaning. So if you have two states of the finite dimension in different spectra, then the entropy of, say they have both the same, so the rank is the number of non-zero eigenvalues. Let's say this is the same. Then really, when you compare the entropies and the entropy of the second one is larger than the entropy of the first one, then this tells you that you can have a unitary that transforms rho to rho prime and leaves your catalyst unchanged. So this is a conjecture that we are not able to prove, but it would be very interesting, and it would give the von Neumann entropy a new meaning just in the context of unitary quantum mechanics. Now what we really found unbelievable is even the classical version is completely open. So classically, if you just look at probability distributions, you say, well, I have my probability distribution P, and I have a catalyst Q. I do a big permutation on both of them, and then I want to get back my catalyst. And on the first system, I want to get the other state. When can I do that? Answer, if and only if the Shannon entropy goes up. Yeah. That seems to be true as well, but it's not proven, and nobody seems to have looked at this. And we've tried like half a year to prove it unsuccessfully, so if you're bored on one afternoon, you can sit down and have a try. But maybe you can see the appeal of that, because it would give von Neumann entropy really an interesting meaning and an interpretation. Okay, so let me stop here. So what I've first shown you is that the usual interpretations of free energy and of von Neumann entropy, they're only meaningful in the thermodynamic limit. You have many particles. Or information theory, you have many copies of your state. Now I've built here on the resource theory approach, and when you do that and you do the usual notion of catalysis, then you will find that you get these extra second laws, these additional constraints that all these infinitely many alpha free energies have to go up in your process. But then I've shown you that if you allow correlations to build up in a way that in some situations doesn't matter, in others it may, but if you allow that, then in fact this restores the standard second law in its usual form. So this gives the free energy an operational meaning for single particles in this sense. And then I've shown you some conjectures how some related results in quantum information theory would wait there to be found. Okay, that's it. Thank you.
Just on Bennett's puzzle, I'm just going to get some insights to why it's puzzling. I mean, the normal way one thinks about Lando's principle type situations would say, if I've got 2 to the n bits in which I can store information, I know for sure the system is either in one of 2 of the possible memory configurations, but it's definitely not in the other ones. The normal way we think about Lando's principle, that's an enormously more useful resource than just having a 1-bit memory component, which is in one of the other those.
Yeah.
So, I mean, should I be surprised that if I have this very large, definitely empty memory, I can use it to do things that I couldn't at all do if I just had a single memory?
Well, it's a bit of taste whether you should be surprised, I guess. But maybe it's more surprising if you think of it in doing it this way. So let me maybe go back to it. It's fast enough. So what you can say is you would say, let me choose my epsilon really small, like 10 to the minus 100. Yeah. No, sorry.
But n is really big.
Here. So n is very big. And then has to be really big, yeah, sure. But, well, not sure if 10 to the minus 100 is so illustrative to think it really intuitively, but say ridiculously small epsilon. Yeah. And then obviously the n has to be taken very, very large for that puzzle to make any sense and to give you delta S larger than 0. But let's make it really ridiculously large, but still finite. Now, what you have is in this process, you do this process and then you measure, is it really in the first one or not? With ridiculously high probability, you'll find that yes, obviously it's in the first slot. So the probability can so be ridiculously close to 1 that you can really trust it. And what you had is you had n, so you had a resource with n minus 2 empty slots, and you made it into a resource with n minus 1 empty slots. With a probability where you can really bet your life on it. Yeah. So still, I mean, it's really big, the system, yeah, so it's quite surprising, and it's somehow interesting to see that the alpha free energies would rule that out.
So I take it, it's not as if being the fact that I can do this doesn't in any way let me get around Lando type. Even if I did have the power to do this transformation, it's still the case presumably that fantastically big memory that I had as empty was already a resource I could use to do.
Yes. So, I mean, this is not really a paradox for anything that we know about standard thermodynamics. Even it's true. Yeah.
Okay, I see the curiosity of that.
Yeah. Yeah.
Okay, thanks.
Goes somehow against intuition. I'd say. Yeah.
Can I just make a follow-up? So Judea-Pearl has a nice criterion for what you count as a satisfactory resolution of a paradox, which is that once you've got it, you should be able to go back and see why your intuition was mistaken. So in that sense, I don't think you've really resolved this paradox. So I didn't share your intuition that this should be impossible. And I don't think it's the case that when you look at your resolution, saying, well, it's about all these conditions, that you can go back to your intuition and say, what I was mistaken about, the reason I thought it was impossible was because implicitly I was assuming catalytic conversion, not non-catalytic conversion. But when you expressed your intuition, there was no mention of whether catalysis or failure of catalysis was involved. So it seems to me, unless somebody, a priori I have no intuitions about whether this should be possible. You work it out for the catalytic and the non-catalytic cases, you get the answers. I didn't have strong intuitions either way.
Well, so first of all, obviously, this is not my goal here to solve that particular puzzle. I was really just trying to illustrate what these alpha conditions can give you in some cases. Yeah. And obviously, it is not a paradox. Yeah, it's not. If you have many copies of the left-hand side, you can go to many copies of the right-hand side. Yeah, you can. Or you use these correlating catalysts that I talked about, you can really do that. Right? So it's not in that sense, a paradox. Still, I think if you think at the one-shot situation, like you're just born once, and you only live to ever do this experiment once, and then you pass away. Yeah. Then what this tells you is you can really, if you could do it one shot, yeah, without any other changes in the world, then it would be, I would still think that would be really surprising. Yeah? And the resource theory tells you cannot do it in a one-shot manner. Yeah? So really to do these transitions, you need many copies of the first, you need many copies of the second, and ridiculously many, and then you can do it. But if that's all you can ever do, and you do it only once, and then if the epsilon is really small, that's the only thing that matters to you. If it's 1 in 1,000, it will probably work, and then it's done. Yeah? In the single-shot case, I still find it surprising. And in the single-shot case, without having any other changes, including correlations with other systems, it's indeed impossible. It's a bit the intuition, no? But again, yeah.
Other questions?
Maybe a really basic question, but I was confused when discussing the process to heat in this quantum system. You said that the goal was to heat from a finite, from a ground heat from temperature T to infinite temperature, but it seems like you're describing just heating it from T to T plus some value. It doesn't really seem like you've got an infinite temperature at the end. I was confused. I was like, does infinite temperature, maybe I just went to misunderstand how
Yeah. I mean, so here it's just a state that I want to get. Yeah. So it doesn't really matter that it's infinite temperature or what. You just say that's the state I want, can I do it?
Yeah. Well,
but regarding
infinite, that's I
yeah, so the thing is that if your temperature is finite, you will always have a higher occupation probability for the ground state than you have for the excited state. And once temperature goes to infinity, it really becomes equal. So in that sense, that will be infinite temperature.
Okay.
Near the end of your talk, at the very end, you showed these two parallel conjectures, which seemed to have quantum version and classical version. They looked totally analogous. But then just prior to that, you made it seem as if your result, that the intuitions about this sort of result would be different depending whether you're thinking about it quantumly or classically.
That the intuitions would be different?
Yeah, like you had a slide where you said it's exactly the opposite. And so not this part, but earlier, going back further.
Exactly opposite.
Keep going back.
Further. Back, which part?
Yeah, in the new one-shot interpretation of free energy.
Okay. Maybe for work costs, or the one before, maybe this.
I'm not sure where it is. There's a slide where you said the core mathematical result here is px tensor py prime is majorizing pxy. Yeah, this one.
Yeah.
And then the very next slide you sort of said, well, this is not what you would expect from a quantum perspective. Am I right about that?
Oh, no, so I talked about something surprising there, but surprising
I see.
every way.
That's not relating to the previous slide. Okay.
No, it's something new. All I said is, hey, standard thermodynamics with standard free energy tells you systems with correlations have more free energy than systems without. Yeah. So if I pump in correlations, increase the standard free energy from left to right. So I think that this makes it even harder to do the process. And the surprising thing is that it makes some transitions easier here. Yeah, so standard thermodynamics just will tell you that this makes it even harder, but here really helps you. That's the surprising thing here.
So does this have to do with the fact that the conditional entropy quantum leap can go negative?
No, this is more related to the fact that this inequality is just wrong for the other f alphas.
Oh, I see.
So for the other alphas, so this is called subeditivity here. Yeah. That you just look at the system separately and then you add up the free energies and it's less than the total free energy. Actually super additivity, I should say. Yeah. It's called super additivity, and the other f alphas are not super additive.
But I think it is related to the negativity of the conditional. Because if all the energies were the same, this would just be saying that correlated state could have entropy 0 even though the marginal have non-zero. Think about that, right?
So this is block diagonal, so it's basically classical here. So that's why I don't think it has something to do with it. It's about subadditivity, mostly.
Sorry, this is related, but this might be also where I know you put these. The correlations they can be classical, so they don't have to be quantum.
Yes. Again, this is all so far proven in the case that I mentioned here, where all the states are block diagonal. So, where did I say it? Hopefully I say it here. Block diagonal energy. So these are really diagonal matrices, so you can just read them as occupation probabilities. If you have coherence in the game, then it becomes a bit more involved. And we think there is a version with coherence, but it's a bit subtle about what's possible and what not. And there, I think you do need entanglement, not just classical correlations.
Can you go back to the slide about stochastic?
Oh yeah, where was that later? Yeah.
So I guess the motivation of this paper is to say that I'm allowing I'm enabling a transition by creating correlations within the catalyst itself.
Yeah.
But since the free energy of that correlated catalyst is actually larger, then you're not exactly stealing from the catalyst. At least according to the free energy measure. However, the question that I had in mind was what happens if we think of it from a very operational perspective, in the sense that what happens if I insist that I would like my states to be, I would like the correlations to be destroyed? Is that for free or do I
No.
need to?
So this is a good question. I mean, the thing is here, this is a very different setting, because here you cannot reuse these systems. Yeah, they are just stochastically independent. You do this once, and then they're used up. So that's why the paper was called stochastic independence as a resource. You have stochastic independence, and you kind of burn it and then it's gone. Yeah. So I shouldn't even call these catalysts. It's like an extra system. It's like a big oven where you put in, instead of coal, you put in stochastic independence, and you burn it, and then you get up correlations, and then it's over. Yeah.
So with this stream of particles, then we can think about it as in the scenario when we have a stream of particles
Yes.
coming in and forming the reaction, then we are actually bringing stochastic independence in continually as a resource.
Exactly.
Therefore,
That's a good way to see it, yeah. So in fact, we got this result when we were trying to prove the other one. Yeah. So this is not really what we wanted, because that's not a cyclic process. Yeah. Whereas the other one can be seen as cyclic to some extent. So when you think of this machine here, let's just, where is it? There's a picture. Yeah, here. No, yes, here. So in a way that's cyclic. It's cyclic in the following sense, namely, locally your machine stays exactly the same. Yeah? But you assume that whatever comes in, and that's fresh new stuff, is initially uncorrelated, exactly. And so in the old picture, that would be a resource that you also get, would be this initial independence. And it's a real difference here, because here you can really say, well, maybe I have this biological machine, I just act on these particles once after the other, then this is fine for me, this is cyclic enough. But obviously in the other case, that's not cyclic enough. You can do it only once and then you're done. Yeah, you've burned your stochastic independence, and then, where is it? Here. And then it's over.
I mean, I find it interesting because this kind of tells us that bringing in fresh tensor products can act as a resource.
Yeah.
But also, intuition also tells us that if we have correlations, we can exploit these correlations.
Yeah.
So,
Yeah.
is it both?
I think both can be a resource depending on the circumstance. I think correlations remain a resource if you have many copies. Yeah. In the thermodynamic limit, because then you find the standard prescription of the free energy, and they still tell you that it is a resource. Whereas in the thermodynamic limit, stochastic independence loses its resource character in all situations. Maybe that's a way to see it.
Rob, if you have one more.
Sure.
Go on.
So this is very interesting. Do you believe that this notion of catalysis, where you allow correlations, is a better mathematical representation of the intuitive notion of catalysis that you just see in old thermodynamics textbooks, which says, oh, you can always use the machine over again? Because in some sense, if you just ask, what do I need to be able to use this machine over again? Do I need the correlations with everything else to remain the same? No. If I'm only interacting the machine with the next system, those other systems are not involved. It seems not. So would you go so far as to say this is sometimes the right way of mathematically formalizing the intuitive notion of catalysis, and therefore the lesson is that all the usual thermodynamic relations do apply to single-shot regime?
No, that's not what I would say. Absolutely not. I would say it depends really on the task you have in mind. Because the task here, if you think of this little biological machine, then, just taking this intuition one step further, if it's really biological, it does something quickly to that particle, then whatever you do here will typically create correlations. It's very hard to avoid fully that in the end you have correlations. So in many cases you will get them. But they have big disadvantages. For example, maybe these systems here later on, so for example, if they're strongly correlated, you want to heat them up, like 50-50 probability for up or down, but maybe they are so strongly correlated they're actually all up or all down. Yeah? And maybe if these have to do with the working of something in your body, and you want that it's robust under errors, and if you have 10,000 of these molecules working in your bone somewhere, maybe some of them should collapse and others not, but here maybe they all collapse individually. So it may be a big disadvantage to have the correlation between the individual systems mediated by the machine, depending on the task you have in mind. Yeah. I guess that's something.
One could make the correlations arbitrary.
You could make them arbitrarily small, but then you would really need a really large catalyst. And even if you have them small, you would kind of still, enough particles would still collect them up somehow. So It's always a trade-off to be made where you can trade one thing for the other, like smallness of the catalyst versus size of the correlations and so on.
So there's something I'm missing here, which is if that stream of particles is considered as the systems I'm doing work on, then in the standard way, if I imagine building a heat engine, it's going to put marbles on a shelf. Marble 1 comes by, put it on the shelf. Marble 2 comes by, put it on the shelf.
Yeah.
There's kind of nothing in the description that suggests that in the future, all those marbles I lifted earlier are going to come back and I'm going to do operations on them, and the fact that they're correlated is going to be relevant. That was just, there's nothing in the definition of the problem that suggests I'm ever going to see those marbles again. So why do we care about that correlation?
Well, it really depends on the context in which you do this transformation. So suppose you want to use this machine to, maybe you're very bad in deciding in the morning what kind of breakfast you have, okay? We have two kinds of breakfast. Sometimes you have oatmeal and sometimes you have cake. And you want to make sure that sometimes you have oatmeal, sometimes cake, quite unpredictably, but in a mixed way so that you don't get bad digestion. Yeah? Not always oatmeal, always cake. So then what you do now is you say, well, for every day I have now a marble, or like a coin, and let it prepare by this machine. And, so I always have, like, there's oatmeal, or there's cake. And it's always 50% probability. And it's put into little boxes, and every morning you open one of these envelopes, and then there's the next one next day, okay? And then, randomly, if you just look at one single day, then yes, randomly 50% it will give you a cake, or 50% it will give you oatmeal. But if you have very strong correlations, and maybe you have n of them, and they might be so strongly correlated that, in fact, they're all the same, all cake or all oatmeal. And I guess that's not what you want. The first day you open your first envelope, oatmeal. The machine worked very well, it randomized, I didn't know what happens, very nice, you eat it. Second day you say, oatmeal again, oh well, okay. But then after 100 days, he will be really annoyed. And so this would be a task that would this would not be helpful. And I guess, depending on where you want to use that and how you want to combine these systems with each other, what kind of task you want to accomplish with them, it's okay or it's not okay to have the correlations.
Other questions?
This is probably something I would be able to answer myself if I've been tracking the technical details, right? I've sort of lost memory of how much of what's going on here is because of small systems in single-shot aspects, and how much is quantum mechanical versus classical. I don't know if you can sort of disentangle that, so to speak.
Yes, so all I said so far you can read fully classical for discrete classical systems. So just have probabilities of configurations, and I don't know which of the configurations I have. In the quantum case, you have to deal with more subtle questions, and Nelly talked about this. The problem is in the quantum case, we don't have these nice Lorentz curve pictures to tell us whether thermal transition is possible or not, but it's much more involved. And then it's really open so far with this theorem that I've shown you that you can do this for the free energy, whether that's possible or not. And right now it seems that it's in a subtle way impossible. You need an infinite dimensional machine system, it seems, in the quantum case to really do it. And then the question is that fair or not? Can you really control these infinite dimensions and so on? That's very subtle. But all that is in principle, that I've shown you, in principle classical.
Other questions? Okay, let's thank Markus.
Thanks.